Okay, so I'm sorry for the technical delay. My name is Pavlo or Pasha Gavrylenko, and I will teach you equations of mathematical physics. Uh, so uh, First, I would like to ask you to write your names and emails so we can contact each other. And I would also like to ask you to tell your names. Maybe I will not remember this for the first time, but I will ask later and probably I will learn at some moment. So. Uh, So and paper. And also, if you want to contact me, my email is this one. This number is the number of my school in Kiev. Uh, You can you can see it sometimes in the people's emails. Mm. So please write here if you have any questions and or whatever. Uh, could you tell in a few words what are your names and what are you doing? What are your interests in science and, and so on? Mm. So, uh, please tell me what are your names so that I know. Hmm? 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 Mhm. Thank you. Ah, see. Mm. Thanks. Mm. Thank you. Mm. Thanks. Ah, see. Thanks. Mm. See. Thanks. Ah, thanks. Mhm. Mhm. Thanks. And you? Mhm. I see. Thank you. So, uh, and I'm originally a physicist, and then I also had math and mathematics, but anyway, I'm still a physicist. So. Mm. Probably some things which I will tell will not be too rigorous, but if you don't like something, ask any questions. I I can try to make things more mathematical. Uh, Okay, so also one technical question is about recordings of the lectures. So you see, I've put the tripod with a smartphone, and now it's recording. All these four blackboards, and as a result, quality can be not so good because only one quarter will be mm, uh, actually used at any moment of time. If someone wants, you can put this tripod closer near you and rotate it to record one blackboard at a time. So I understand that it can take some attention. So if no one cares, we can leave it as is. So, but if someone wants better quality, you can do this. Uh, mm. Mm. Yes, I've received some email that I should register in Teams, but at the moment I have no idea how to do so. I asked how it works. But what? So why is it useful? Like, what can you find in this Teams? Ah, so my original plan was to put it somewhere on YouTube, but it was. Well, I'll ask someone how to do this. But, oh, mhm. Mhm. Oh, I'll ask, for example, to which channel to put it, and so on. Uh, by the way, and this is my email, and also if someone is using a Telegram, there is also a Telegram account in this one. Uh, okay, so let us maybe start with the main topic. Uh, uh, so equations of mathematical physics. I'm actually not sure that we need some detailed introduction because many of you, I think, already know a lot of examples of such equations. But the main point is that a lot of processes in nature are described by nonlinear equations with partial derivatives. For example, uh, the wave equation. In 1 plus d dimensions. It looks like this. Maybe better to write it this way. And the function of n plus 1 of d plus 1 variables which satisfies this kind of equation with partial derivatives. And this is also called D'Alembert equation. And this operator written here is sometimes denoted by a box. It's called D'Alembert operator. Also, a heat or diffusion equation. Again, in 1 plus d. Poisson equation, which actually I'm writing here 0 in the right hand side, and in this cases it makes sense, but although maybe it's better to put some arbitrary function even now. But there are cases where the most meaningful problems are those which have something in the right hand side. And for example, this is a Poisson equation. Which is actually let us introduce Laplace operator here. So it's d over dt minus Laplace n. Question of u equals to 2 minus rho. So there are also more complicated nonlinear equations. For example, mm, mm, so which one shall I write? For example, Navier-Stokes equation. Mm, plus some viscosity term. Mm, and so on. Uh, well, probably maybe I should also list uh, two more equations which are still linear and which appear in physics, just because we'll see them immediately in the classification. So one equation is a Helmholtz equation. Forgot if there is T here or not. Like Laplacian of u equals to lambda u. And as you see, there are sometimes equations of this kind with a metric with a 1 minus 1 minus 1 minus 1 but they have analogs with all ones in the quadratic operator. They correspond kind of to Minkowski and Euclidean space-time. So there is an analog of a Helmholtz equation, which is a Klein-Gordon equation. Which looks like a D'Alembert operator um, plus m squared times u equals to 0. And this is the equation describing a relativistic massive particle in maybe I would say in quantum mechanics, but it's more correct to say in quantum field theory. So there are a lot of nonlinear equations in physics, but they, of course, appear also in pure mathematics. For example, there are equations like, maybe I'll write it here. I don't know. There are equations like a Liouville equation. which is a two-dimensional equation vector phi equals to e to the 2 phi. This describes a matrix of constant curvature on some domains, or more generally on some Riemann surfaces, if find a way to write it globally. There is also a lot of integrable equations, like, for example, KdV equation. Maybe let me write it this way. So originally it described waves in the shallow water approximation, but it also turns out that first it is integrable, like we can write infinitely many solutions of this equation, and actually this exact solutions are dense in the space of all solutions, in a sense that any solution can be approximated by some exact solution of KdV. And but it's not the only thing to know about it. It's also important that it appears in many purely mathematical physical properties, problems, like some enumeration problems in some enumerative geometry. So a lot of objects generating functions satisfy this equation and also other equations of the KdV hierarchy. So probably I will look at it at the very end. But the most of the course will be devoted to linear equations. Which can be in principle solved for any initial data or any right-hand sides, unlike nonlinear equations, because in the most cases we have only some dense subsets of integrable solutions. They are more complicated, and we need different methods to solve nonlinear equations. Okay, so are there any questions about the motivation? Okay, so let us start with something more concrete. So this is that a lot of equations are partial differential equations of order not more than 2. There is actually some physical explanation why these equations, which describe something more or less fundamental, cannot have higher orders. This is because they follow from some Lagrangians which do not have higher derivatives. But technically, we just see that most of these equations do not have higher derivatives. So, so it is natural to consider the following problem. So let us have a generic a linear equation with partial derivatives, which has this form. Let us write here Jij plus some. So this is a constant metric, and what is written here is kind of Laplace operator in this constant metric, plus some vector field acting on this function from 1 to n, plus some constant times u. So now we can now we want to bring it to some canonical form. And to do this, we perform linear transformations, like xi equals sum over j, some cij, maybe tij, x. I'll make all indices lower. So, does anyone know what can be done with this matrix with such a transformation? For example, how does it transform? Maybe the first question. So x tildes. And vice versa, xj tilde is equal to sum over xi tilde is equal to sum over j t inverse ij xj. So let us try to write partial derivatives in x in terms of partial derivatives in x tilde d over d. xi is sum over dxj tilde over dxi d over dxj tilde. And if you use this formula, we see that maybe let us make this t inverse and this t. Maybe it's easier. So here we see sum over t ji d over dx j tilde. And if you substitute it to the first term of the equation, we will see that it is sum over sum mn And if we collect this together, we see that this was our Laplacian of u. Laplacian of u equals to this one. All of them act on u. And it equals to some other matrix J tilde. J tilde mn d2 over dxm dxn, where this matrix J tilde mn equals to j and ij, sum over ij. So if we write it in the matrix form, we see that this J tilde equals to T J T transposed, which is of course a correct transformation property of a matrix of quadratic form. So now the question. So if we are allowed to use any invertible matrices T, what is the canonical form of real symmetric n-by-n matrix which can be obtained by such transformation? So who knows this? We can think about this in other words. So this matrix G defines a scalar product on n-dimensional space. And this is used to multiply the vectors of derivatives, d over dxi and d over dxj. And then we are free to choose the basis in the space in any way we want. So what is the best choice of basis? For example, do you know about Gram-Schmidt procedure? And what is it used for? Hmm. Oh, yeah, let us maybe start from some simple example. Let us take some operator like so a d over probably I'll use dx squared plus b dx dy plus c dy squared. So I don't know. Is it possible to bring this operator to a form of a sum or difference of squares? Like, if we want to get something of this form or of this form, what can one do with such an operator? Who remembers Gram-Schmidt procedure? What is it about? Yes, of course. Uh, and uh, uh, and what is the result of it? So and how it goes. So we originally we have some vectors such that their scalar product E J equals to some matrix Gij, right? Uh, then we take some vector with a non-zero square, take, for example, E1. Suppose that, just take some vector V1, so that V1 squared is not equal to 0. And then subtract it from all other vectors. Construct uh, V2 equals, no, maybe it's, sorry. What to say that we had some bases which gave some matrix, and then we want to find some other bases. No, actually, okay. Let us maybe say that we've chosen some bases in the general position, and forget about these special cases. Okay, so we take the first vector and say that its norm is non-zero, and then we choose all other vectors orthogonal to this one. Like I say that V2 equals like V k equals E k minus E k. It's for k greater than 1. Ek E1 over E1 E1 here is E1. So these vectors are orthogonal to E1. Just by construction, because we can compute this scalar product and see this. Then we take a vector V two, and we define vectors with oh, So concerning the notation, so we already have a vector E1, then we have vector V1, which is orthogonal to this E1, and we need to construct and we have a bunch of vectors which are not orthogonal, which are orthogonal to E1, but not orthogonal to this V1. And then we make them orthogonal also to V1 by subtracting the same object. Let us say that for k greater than 2, we define V. Sorry, it's V2. We define Vk prime, which is equal to Vk minus maybe Vk1. And so constructed a vector, the first vector from this set V3, 1, is orthogonal to both of them. And there are also some vectors which are not orthogonal between each other, not orthogonal to V3, but orthogonal to these two vectors. And we repeat this procedure, like we k2 equals to vk1 minus v31 vk1. Sorry, this notation is super stupid. I I didn't prepare for this, but I think the idea should be clear. So and so on. And in this way, we construct vectors which will be orthogonal to each other. It might happen that at some moment we end up with vectors which all have zero scalar products, and so it will mean that the rank of this matrix is less than dimension of space. But the result of this procedure is that we get some basis in which so let us call this all these vectors Fi's. So in this way, we get some vectors such that Fi, Fj, scalar product, equals to some Ci delta Ij. And also we can rescale these vectors so that Ci is equal to plus minus 1 or 0. So canonical form of this metric is 1 is some number of maybe minus ones, then ones, maybe 1 minus ones, and zeros. P of this, Q of this, and minus P minus Q, Q of this. And of course, this is quite this can be applied also to this quadratic differential operators, because they're described precisely by the same object, by metric in two-dimensional space. So this changes of this change of basis from E's to F's is precisely this change of basis from X to X tilde. For example, if we want to do something in this a simple case with two variables, what can we do technically? We can find a complete square here, like write that it is a dx plus b over 2a d, dy squared minus b squared over 4a maybe let us write this way. So we see that we can find variables such that this variable is dx tilde, and well, and that's all actually. So we want such variables that dx tilde is dx plus b over 2a dy, and dy tilde is dy. And now a question to the audience: who can write such variables? Like, what should be the relation between x x tilde y tilde and x and y, so that we have such a relation for the first derivatives? We have found a way to reduce this differential operator to a sum of squares of two differential operators. Now the question is, what is the change of variables which turns this operator into just a derivative in some variable? And the question is, who are x tilde of x y and y tilde of x y? If you don't want to think about matrices and inverse matrices, there is a simple way to get such formulas. So we know that in this new variables dx tilde acting on x tilde is 1, dx tilde acting on y tilde is 0. And now if we remember this formulas and the old derivatives, and also dy tilde on acting on x tilde is 0, the y tilde acting on y tilde is 1. So if we write it in the old variables, it will mean that dx plus b over 2a dy acting on x tilde is 1, acting on y tilde is 0, acting on uh, and dy acting on x tilde is 0, dy acting on y tilde is 0. So, is 1. So there is a set of 4 equations which defines the new variables x tilde and y tilde. And how would you solve such equations? Mm. Example, x tilde is defined by this equation and this equation, and so this one tells that mm, x tilde does not depend on y, and this equation tells that x derivative of x tilde is 1. So uh, so what is the problem to find x tilde? Does anyone have any idea what can it be? Yes, precisely. Yes. So it's the first part of the answer, because we can simply look at this equation. For x tilde is some linear combination of x and y, but if y derivative of x tilde is 0, it means that it does not depend on y. So it depends only on x. And now look at this equation. This derivative is by 0 because we already know this, and this derivative says that x tilde um, is x. Actually, it can be shifted by some constant, but we don't care. We need just some example of such coordinates. Thank you. And, the question is what about the other variable? What is the formula for y tilde? No, it does not work this way because look at the last equation. Y derivative of y tilde is 1. And if you... Hmm? So... Hmm. Yes, thank you. So, is it clear? Like when the answer is written, is it clear that it solves these equations? So, uh, of course we could get it from such formulas. We know the matrix which transforms one coordinate to another coordinates, and we could just take inverse. But usually it's easier to do this way if there are some simple coordinate transformations. The consequence of this is the following: that for any a, b, and c, and that a is non-zero, this operator in these coordinates can be written as a dx tilde squared plus c minus b squared over 4a dy tilde squared. And now, dependently on the sign of this of this term and of this term, this can be either a assumption of a form dx. We can still scale these variables further to remove numeric coefficients. So this can be the dx squared plus dy dy tilde squared just dx squared if this coefficient is 0. Well, I would just put different signs here and there. So in principle, each of these terms can have either a positive or negative sign, or this term can be 0. So it's an illustration of this classification theorem that matrices in two-dimensional space can be brought either to this form or to this form. Like I've said, matrices quadratic forms, or this form, or this form. Well, of course, there's an option where it is just 0, but it's not interesting. And so probably we'll make a 10 minutes break, right? Because or do you need any break or not? So yes.
So what we are trying to say is that if we have pure second order operator, and so we do not have any other kind of differentiations, we can write it in a canonical form, which is only of sums and differences of pure derivatives in only one variable.
Well, in different variables, but they're squares.
Yeah, that's
So,
right.
yes, yes, of course. So now I was telling about operators with constant coefficients, and if we work in the generic case, in the arbitrary dimension of the space-time, it's the only, probably the only way we can proceed. But if we work in two-dimensional space, the same is actually true, almost true for operators with coordinate-dependent function. The meaning of this in that metric in 2 dimensions can be brought to a canonical form, like some function times a flat space plus operator, like metric in 2 dimensions can be made diagonal by some change of coordinates. I don't want to tell this now, but probably I will try to tell this at some moment later. So. Yeah, and then we will switch to this last part of equation and see what can be done there. But by the way, do you know, is it normal that it is so hot here? Can we do something with the air conditioner? Thank you. Okay, so let us continue. So what we know at this moment in that this first term of differential operator, which contains a metric, can be brought by Morley's Gram-Schmidt procedure to a canonical form, which is a sum of a sum of squares minus some other sum of squares from I equals to 1 to p, the squared u over dxi squared minus sum from I equals to p plus 1 to p plus q, the squared u over d xi squared. Let me actually call this number r. Plus nothing. And here we have some first derivatives with some other, like I'm using here x's, but these x's are of course some linear combinations of initial variables. I just don't want to keep this tildes. Just remember that we have already changed variables to make this part canonical. Plus sum from I equals to 1 to p plus p plus q plus r vi d over dxi du plus some cu equals to 0. Okay, so now we want to do something with this term. But things we can do, of course, depend on this first term. So before we're changing coordinates, but now let us try to change the function itself. Namely, let us consider some other function u tilde, which is related to u by this transformation. U in terms of u tilde equals to e to the 1/2 sum from I equals to 1 to p vi xi minus sum of I equals to p plus 1 to q vi x xi times u tilde. And now let us try to compute the second derivative of this expression in, for example, x1. So, namely, d over dx1 squared of u equals to So when we differentiate this, we so let us call this exponential like e to some phi times u tilde. So this first oh sorry, actually no, it's fine. So d squared over dx1 squared consists of two parts. First we take the first derivative. And the derivative differentiates phi and also differentiates u. So it is d phi over dx1 e to the phi times u tilde plus d phi over, plus e to the phi and du tilde over dx1. When we take second derivative, let me write from the very beginning that it equals to v1. And I actually missed here the sign. I would like to put it in this way. This equals to minus v1 over 2. Then differentiate it once again. So it is d over d dx1 minus v1 over 2 e to the phi u tilde plus e to the phi du tilde over dx1. And we can either differentiate phi here. It gives another such factor, v1 squared over 4 to the phi u tilde. Or we can differentiate u tilde here, minus v1 over 2 e to the phi du tilde over dx1. Or we can differentiate e to phi in this term, which gives exactly the same expression, v1 over 2 e to the phi du tilde over dx1. Or we can finally differentiate this first derivative in the last term, plus e to phi du tilde over dx1 squared. So finally, so what have we achieved by this change of function? We see that altogether these two terms give minus v1 e to the phi du tilde over dx1. And this term will cancel this first order derivative which was in this sum. So namely, let us compute the sum of these two derivatives. D squared over dx1 squared plus v1 d over dx1 acting on u. It consists of this term which we have already computed. So it is v1 squared over 4 minus v1, let me put it in this way, plus this term coming from the first order derivative, plus v1 e to the phi and here we have minus v1 over 2 plus d over dx1 u. So now look at these two terms, this one and this one. They coincide, and so they cancel. And finally, oh, so it's u tilde. So finally, we get an expression like e to the phi d squared over dx1 squared minus v1 squared over 4 times u tilde. So technically, what happens, or not technically, ideologically, we again do the same procedure. Like we try to find a complete square in this differential operator, and this complete square looks like this. It is d over dx1 minus v1 plus v1 over 2 squared minus v1 squared over 4. So this operator equals to this one. And now, so when we wanted to perform some linear transformation of first derivatives, we were changing coordinates in a linear way. But here we want to perform some shift with these derivatives. And to perform this shift, we can do this. We can check that a conjugation of some e to alpha minus alpha x dx e to the alpha x equals to dx plus alpha. This is precisely what is done here. And this identity is easy to check. We just substitute here arbitrary function f and compute these derivatives. E to the minus alpha x dx of e to the alpha x f equals to the term when x when dx acts on this exponential, and it equals or maybe first act on f, it equals to dx f, and when it acts on the exponential, it gives alpha f. So this is precisely what is done by this change of function. So is it clear what happened? So a result of this computation is the following: that result So this equation for U tilde has this form. So this last term changes. Here we have only sum over coordinates which uh, are not present in the first two sums. So the sum from p plus q plus 1 to p plus q plus r du over dx some vi's du over dx i's plus some other du tilde plus some other constant. Is it fine? Are there any questions, or is everything clear? Okay, so let us proceed, maybe. Or, actually, I don't understand. Is everything clear or everything unclear? So,
So on the PDEs we treat, you have each kind of derivative, partial derivative, only one time. So if a partial derivative with respect to x occurs in the second order, it will not be present in the first one.
yes, precisely, because of the streak. So it is true for let me think. It is true for operators with constant coefficients, and in general case, I think it will not be true, because geometric meaning of all this is the following. Here we have a metric, and here we have some vector field, and actually, oh, I need to think, but so if you multiply, uh, if we multiply our u by some function, in the general case, when all these things are coordinate dependent, we will get a correction which equals to derivative of this function, and we will need to cancel this vector field with derivative of a single function, and it's generally impossible, because if you have equations like df over dxi equals to vi, which depends on x, we need to satisfy mixed derivatives relations like di vi should equal to dj vi should equal to di dj di vj, and in general it will be impossible. So so all this works for for operators with constant coefficients. And actually, what I'm saying is absolutely identical to a classification of quadratic surfaces in n-dimensional space. The only difference is that here the role of coordinates is played by differential operators. Okay, let me erase this Gauss-Schmidt procedure. Yeah, so finally we have this equation, and then we can change coordinates in such a way that this derivative is a derivative in just one coordinate. Because geometrically it looks like this. There is some, for example, plane, and we have this vector v. And we can construct a first-order differential operator from this vector v, which is this vi d over dxi. And this is differential, and this is an operator of derivative in the direction of this vector. So, in order to simplify this term, we just choose coordinates like coordinates in the like one coordinate in the direction of this vector, and the other coordinates in some sense orthogonal to it, like say that, and this is another coordinate, or so that this derivative is a derivative in just one coordinate. So technically it can be done like this. So we have this r coordinates, and we want x, we want some other r coordinates, like x plus x tilde p plus q plus 1, and so on, x tilde p plus q plus r. Find such that this combination of derivatives acting on the first coordinate give 1. Acting on some p plus q plus 2 plus 3 and so on plus r gives 0. Because it is to find such coordinates, because just take any of them and subtract the first one if it is non-zero with the appropriate coefficient. So it is a trivial exercise. You can think about this at home if it is not obvious. But a result of this is that this the combination of first order derivatives can be turned into a derivative in just one variable. So it So this equation transforms to some. I will remove all these tildes and write just current state of equation. Mm. And we can also, here we also scale this variable so that the derivative comes with coefficient 1. So it is dx p plus q plus 1 plus a constant times u equals to 0. Uh, and now there are options. So this term in principle can be absent. If we have r equals to 0, so this is one option here. This is when r does not equal to 0, and this vector does not equal to 0 from the beginning. But it could happened from the beginning that we obtained only these two terms and nothing here. Uh, so one other possible option is that after this procedure we get c equals to 0. It is also possible. So in these two cases, these are final forms of these equations. We cannot do anything to simplify them. But in this first case, it can still be simplified by the change of variables, namely by the change of function. Namely, in this case, we can substitute u equals to u tilde times e to minus c x p plus q plus 1. And you see, when we differentiate it, it will give precisely minus c times u, which will cancel this last term. So finally, we get a very similar equation, but with the first derivative. And this is. with the same summation limits. And it's the end of classification. And there are, of course, corresponding surfaces in this spaces. I don't remember their names. Probably this is called some kind of saddle or parabolic hyperboloid or whatever. And if you look at this equations which are out here, you can see representatives of this classification. So the only peculiarity is that in the real world people always have either 0 or 1 preferred coordinate. In a sense, we have only one time variable, and because of this, all equations which are of practical interest are these ones. Let me, probably I can erase something like initial problem, because I think everyone should remember it. So equations we are going to study are these ones. And maybe if time allows, also this equation, like Klein Gordon. And also, so this was a classification about equations without the right hand side, but in principle, we could do exactly the same, keeping arbitrary function in the right hand side. It is called source or inhomogeneity, and it would transform somehow, like its coordinate dependence could change. It could be multiplied by something, but the form of equation would still be the same. It can also be added here. Maybe I would rewrite it this way: equals to f, and maybe also here plus f. So these are equations of our interest. So they all have a different behavior. We can formulate initial boundary value problems for these equations in different ways. So each of them should be treated independently, but they actually share some properties. And so time is almost over. Uh, so um, probably some announcement of what I'm going to tell on the next lecture. So I would like to start from demonstrations of some ideas, first simplifying this problem to something finite dimensional. Because here we see some problems where there is some differential operator acting on some function. Like it's a good question, which kind of functions we should consider here. Like namely, it seems that this should be C2 functions on some R-dimensional space, but in reality, it turns out that we can do some trick and switch just to integrable functions. But this is some problem which involves analysis. And but a lot of ideas can be actually seen in some discretization of these equations. For example, let us take this first equation, like Laplace equation. So if we have first derivative of a function, it can be considered as a limit, limit delta x to 0, f of x plus delta x minus f of x over delta x. In the same way, we can write a second derivative of a function, df over dx squared is a limit delta x to 0 of on this symmetric expression, f of x plus delta x minus 2 f of x plus f of x minus delta x over delta x squared. So if we try to do this procedure, we get an equation of this kind. So now let us forget about this limit and say that instead of derivatives, we write a finite difference. And this equation looks like this. U of x1 plus delta x. Let me maybe introduce finite shift operators from the very beginning. Like, operator ti acting on a function of x1 and so on xd is u of x1 and so on xi plus delta x and so on xd. And in the same way, if you put T inverse, this is of course operator of shift in the opposite direction. So in these terms, this Laplace operator looks like sum of T Ti Ti plus Ti inverse minus 2 from I equals to 1 to D, acting on U equal to some function. But now the question is, what is the space of functions where this operator acts? So since we allow shifts only on only by delta x, it means that it only connects points of the form so this vector x has a form delta x times z to power d. In a sense, all coordinates are proportional to delta x. And at this moment, so this is function defined on such discrete lattice. And actually, if you want something really simple, finite dimensional, it is better to put this lattice on a torus. In a sense, consider periodic boundary conditions for this axis. Namely, to say that how to draw this. So I will draw it like this. So let us put this lattice on a d-dimensional torus. So this is closed from here. And we also close it in this direction. And we also forget about this delta x. Let us put it equal to 1 for simplicity. So it means that we can switch from this space of functions defined on RD to, so in this case, our function is just a space of functions on on a periodic lattice, like z over n1, z times times z over n d z. This is just functions on a finite set, and this is of course isomorphic to uh, 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 to a vector space of dimension nx times or n1 times and so on n d, or it is also naturally isomorphic to the tensor product cn1 tensor c n d. And this operators naturally act on this space. So I will show the some main ideas in this example, and it will be the next time. So, are there any questions? Yeah. Or should they change something or not? Oh, that is fine. So that's all for today.